Okay, our second focus on physical properties is solubility. So we're thinking about whether a solute dissolves in the solvent and to what extent it dissolves. So we might compare two solutes and say that one is more or less soluble in water than the other, or perhaps in oil, a nonpolar solvent, as compared to the other. So when you think about solubility, focus on polarity. It all has to do with the polarity of the solute and solvent particles. So there are three, I've starred the 3 points here that are really important. A solute dissolves, or you could consider will be more soluble if the solute-solvent attractions are strong enough to overcome any forces of attraction between solute particles and then within the solvent, so between solvent-solvent particles. So the solute has to attract the solvent stronger than either solute's attracting solute or solvent is attracting solvent. Secondly, for larger molecules, you may not be able to classify a molecule as being polar or nonpolar because of the size of the molecule. There may just be a nonpolar region of the molecule and a polar region of the molecule. And so you consider the size of these polar and nonpolar regions. And if there's a greater nonpolar region, then it's expected to be less soluble in water, more soluble in oil. If there's a greater polar region, then it's expected to be more soluble in water, less soluble in oil. And the third point, consider the number and location of sites around a molecule that have the capacity for hydrogen bonding. So to have an OH or NH somewhere in a molecule, in a large molecule, doesn't necessarily mean that that molecule will be very soluble in water. If it's a smaller sized molecule and there's an OH present, that will be very impactful. But you do have to look at these larger molecules and look all around them. So look, left, right, top and bottom, and see how water molecules could interact with that solute. Okay, so for this lesson, I've basically created a table now, and I'm leaving the example column blank because I'm expecting you to fill that in either based on your knowledge now or as you learn about different organic families. So since we said the solute-solvent attraction is what's key, I've set up this table to first identify the solute for you, and then you need to fill in the force of attraction that those solute particles experience between other solute particles like them. And then the same for the solvent, and then decide what interaction will be experienced between the solute and the solvent. And ultimately, does that lead to the solubility of the solute in the solvent? So I didn't quite have room in the table, but this is meant to be the solubility. Okay, so we'll start, I'll help you out here at the beginning. So our solute is ionic. So what type of attractions are experienced between the particles in an ionic solid? Hopefully you're thinking that ions make up ionic solids, and therefore the attractions between ions are referred to as an ionic bond. Now for a polar solvent, you might think of water. There's definitely going to be LDF as possibly dipole-dipole, but if it is water, then it will have the ability to hydrogen bond. And so you have to look and see if your polar solvent actually possesses OH or NH bonds in order for it to hydrogen bond. So the question becomes, how does the ionic solute interact with the polar molecular solvent? Well, we have an ion in one particle and we have a dipole in the other, so hopefully you're anticipating an ion-dipole attraction. That's a significant strength, and so we expect most ionic solids to be fairly soluble in polar solvents. Okay, so now for the second one, an ionic solute. Force of attraction is still going to be that ionic bond, but now a non-polar solvent. What type of force of attraction will non-polar solvent molecules experience between one another? London dispersion forces. Okay, so now what type of interaction occurs between ions and nonpolar molecules? And if you're thinking not very much, you're on the right track there, because ions are going to be attracting ions in the solute. There's a very weak attraction between the ions and the nonpolar molecules. And so we see great decreased solubility when an ionic solute is mixed or added to a nonpolar solvent. So essentially we'll say they're not soluble, insoluble. And so you continue to move through the chart, identifying the force of attraction that are experienced between solute particles, the force of attractions experienced between the solvent particles, and then making a decision about the solute-solvent force of attraction. Will that force of attraction be greater than either the solvent force of attraction or the solute, enough to make these substances soluble? If so, you can record yes in the last column, otherwise no. So take a moment and try to complete the table and check in. Okay, so take a moment to look through the force of attraction columns for both the solute and the solvent. I did have an error in the table. I wanted, you'll see I've scratched it out in red, the word non, because we need our nonpolar solute to have an option to be in a polar solvent or a nonpolar. So now I've got that set up properly. And then check out the solute-solvent force of attraction. Ultimately, to complete the last row, you have to decide if the solute-solvent attraction is strong enough to overcome attractions in the other two columns. So in the third row here, we have dipole-dipole or even hydrogen bonding able to occur between the solute and the solvent. That certainly would be strong enough to increase solubility. Now, between our polar solute, we have dipole-dipole, maybe even hydrogen bonding, and with our nonpolar solvent experiences London forces only. So all we have the capacity for between the polar solute and the nonpolar solvent is London dispersion forces, which will definitely be weaker than what the polar solute particles are experiencing. And so we'd expect this to be insoluble, or less soluble, certainly. And then for our nonpolar solutes, they only experience London dispersion forces. So in a polar solvent, the fact that they can only interact by London dispersion forces with the solvent really means that the solvent is going to stay hydrogen bonded in the case of water, or dipole-dipole attracted to molecules like it. And so the two different particles will not mix well. We'll say no for the solubility. In the last case, it's true that the solute and solvent only experience London forces between them, but if that's all that's happening between the solute particles and between the solvent particles to begin with, then that very well will be enough for the solute and solvent to become soluble. And so this answer is yes. So as we go through the unit, come back to this chart, revisit it, and give yourself some examples there so that you get more comfortable with connecting this table to future organic families that we will study. Okay, so for examples here, I've just posed some questions. Okay, you'll see I cut and pasted some pictures here. So in part A, is this molecule here, biphenyl, soluble in water? What would you expect? So hopefully you'll follow the pattern of what we were talking about by first considering the polarity of the solute, right? This is the solute. So what do you think about the polarity there? And the solvent is water. So what do you think about the polarity here? Predict the solubility. So right now we're setting up then the biphenyl to be a nonpolar solute, right, in a polar solvent. And so the LDF that's available to occur between these two is certainly not going to be enough to make the biphenyl soluble in water, and so we say it is insoluble. Okay, try example B. Explain the solubilities as indicated in the diagram below. So you're given the structure of benzoic acid and acetic acid. You're told that the benzoic acid is insoluble in water and that the acetic acid is soluble in water. Can you figure out the difference here and explain the solubilities? Pause the video and then check in. Okay, so I've marked this up a bit. You'll see that I looked at benzoic acid and circled the benzene ring and recognized that as a large nonpolar region in this molecule. And then I circled the C double bond O single bonded to the OH and said, yes, that's a polar area and capable of the dimer effect. So we'll experience an increased capacity for hydrogen bonding. But when you compare the relative size here, that larger region is the nonpolar region, and so this will be dominant, if you will, which makes this molecule insoluble in water. Whereas when you look at the acetic acid molecule, you'll see the same C double bond O single bonded to the OH. So again, polar and the dimer effect for hydrogen bonding will occur, but we have a small nonpolar region. And so in fact, the smaller nonpolar region has less influence, which allows the dimer effect, right? So right here, which allows the ability of the molecule to hydrogen bond in that increased capacity to explain why this molecule is soluble in water. Okay. For part C here, we're going to use these diagrams to predict and explain the relative solubility of ethanol and dimethyl ether in water. Okay, so looking at these two structures, we'll see with ethanol, it has an increased capacity to hydrogen bond. We can see that the H that is directly bonded to oxygen in the ethanol molecule, this is the ethanol molecule right here, that the oxygen on the water molecule can form a hydrogen bond with the H of the alcohol, of the ethanol. And then you'll notice that the oxygen, the red oxygen in ethanol, has the ability to form a hydrogen bond here with an H in water. And so we have this increased capacity to hydrogen bond. Whereas for the dimethyl ether compound, I'll refer to it as the ether, we have the ability for the ether to form a hydrogen bond with a hydrogen in the water molecule, but not the other way around. So we have this ability to hydrogen bond once, if you will, which is a lower capacity to hydrogen bond than the ethanol with water. And so we would predict then that the ethanol would be more soluble in water than the ether. Okay, looking now at a picture of vitamin A here. So vitamin A, also known as retinol, has this structure. Pretty large molecule. So have a look at this molecule and decide whether you think vitamin A is soluble or insoluble in water. Explain your reasoning. Okay, so we see the OH on the far right of the molecule, which certainly is the site for hydrogen bonding with water. As we scan the rest of the molecule, we notice that there are no other polar bonds in the molecule, so no opportunity for dipole-dipole interactions, nor are there any other OH bonds in the molecule. So with just one site for hydrogen bonding in this large molecule and a very large, long nonpolar region, we can anticipate that the nonpolar region of the molecule will dominate its properties and therefore expect that it will be insoluble in water. Okay, the last little bit here is really just a table for you to refer to. It's more just practice. As you look at these structures, there's a continuum from left to right here, starting with a very nonpolar organic molecule as the solvent due to only weak London dispersion forces. And then you'll see that the polarity increases. And hopefully, as you move across these structures, you'll see eventually the capacity for hydrogen bonding over here in each of ethanol, methanol, and acetic acid. Okay, so this is just meant to be an opportunity to apply what you've learned in understanding. Hopefully everything in this table makes sense to you now. The terms hydrophobic and hydrophilic are shown at the bottom here as a continuum. Hydrophobic meaning water-fearing and hydrophilic meaning water-loving. And the idea is that the polar organic and hydrogen bonding capable molecules will be more and more soluble in water. And the ones to the left, water-fearing, the hydrophobic ones, the nonpolar organic, will be more and more soluble in oil, less and less soluble in water. So just an opportunity for you to apply what you've learned and understand this table.